Hey guys, welcome to another video. So today we continue the lessons on binomial theorem identities. So this is the fourth video in the series. So the first three basically covered the common types of questions that I've bucketed into themes. If you haven't seen those, please go forward and click on those before you see this one, because today we're going to basically be doing the harder application. So I picked out two examples from the HSC, which are, there's a lot of marks involved, right? So, you know, an extension one test is out of 70 marks. The two questions I'm going to do today, I think are 6 marks and 8 marks respectively. So, you know, like we're talking about close to, if not over 10% of the test. So if you can't do this type of question, I mean, you're on the back foot. So just to rehash, so the first video that I did on this series covered identities related to substitution, where you basically just sub in values of into x and n, right? And that basically got you your proof. The second video covered questions relating to calculus, so differentiating, integrating. So if you ever see expressions with binomials where the string of numbers has a number in front, the coefficient increases gradually, or has a fraction that increases gradually in terms of the denominator. Generally speaking, that's a calculus related question. And then the last video that we did, the third video, was on comparing coefficients, which I think technically speaking, it's not hard once you visualize it, but it's quite a hard conceptual question, especially for teachers who explain to students of comparing coefficients. There's a lot of layout, right? It's sort of quite horizontal in terms of the space that you need to do to prove it, but yeah, it's considered to be hard technically. So today we'll use a lot of those techniques that we've done in the last 3 videos to do the ones that, well, to do the harder ones we're going to do. So let's begin with this part of the topic now. I think it's fair to say that yeah, these questions take quite a bit of time to do each, so bear with me when I say that it takes a bit of time. So here we go. Binomial theorem identity. So I mean, everything sort of begins with this binomial here, expansion, right? Now you'll see in certain questions today where sometimes the harder ones, instead of having n, they have like 2n or 4n. It's the same thing, right? It's just a longer expansion. So let's state this in terms of the combinatoric expansion as such. X power 1, let's go 2, and then just to help us or help me explain it later, I'm just going to put in the general term in the middle, right? Well, that's like x to power k plus. I don't actually. What I really needed was the a plus b version, but that's fine. Let's put this one in as well. X and there. All right. Now I'll put a little box around this, and I'll highlight it because I'll be referring to this exact box a few times. So what I'm going to do with a bit of foresight, I'm just going to copy that to use in next. Now that's all the theory we need. Let's dive right into it. So HSC 2013. Now you look at this question, and I mean, just the sheer amount of mathematical notation turns people off. You look at this, 6 marks, right? You look at them, and there's a few things that turn people off. Firstly, the summation notation, right? A lot of people don't know what that is, and that's just a lazy way of writing the string of numbers. That's all it is, right? Second thing that turns people, look at this expression, right? It takes a lot to sort of look at that and try to make something out of it. So that will turn people off as well. Even though it says do not prove this, people look at it immediately. Their natural instinct is to go, this is a hard question. So, you know, some people basically come back to it. Some people just get turned off and don't attempt it for the whole duration of the paper. So now let's break it down, right? First of all, we have 1 plus x to the power of 4n. There it is, right? Power of 4n, not just n. So we have to make something of it. But it also tells us, right, in this part here, it's telling me to find the coefficient of x to n. Now that is significant, right? Because when I expand it, 2n is a term somewhere in the middle, right? Yeah, somewhere in the middle. That's important because this expression here is 2n as well. So there's a linkage, right? And generally speaking, whenever you get these long ones where we're proving There's part 1, part 2, where part 1 tells you find the coefficient. It's a comparing coefficient one, right? A comparing coefficient case where we're comparing the coefficient of xn. So I'm hoping that after I do part 1, part 2 and part 3 is going to give me some insight into the longer. Remember how in the third video we had one expression that had one coefficient and the other one had crazy sort of rainbows? I'm hoping and expecting that to happen in questions 2 and 3. You know what? That's enough of me talking. Let's dive right into it. Let me just paste the formula from before. There's a random line there. That's all right. I'm just going to plug that up here for reference purposes. Let's start. So for part 1, right, coefficient of that guy. Now, exactly the same as above, right? In fact, let's be lazy about this, right? I'm just going to go back up a step, copy and paste this guy here. Yep, copy the text, paste it here, and I love doing this to my classes. They just have to watch me do a bit of PowerPointing. So I'm just gonna go black. There you go, done. Now, when I say copy and paste, it was literally copy and paste, right? Because then once you do that, all you really need to do now is to, firstly, let me remove this guy and this guy. Change that to a 4n, right? And then all of these becomes 4n, right? That is seriously all you do in terms of the working out, right? 4n, 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 right? Yeah, now, what are they after? They are after the coefficient of 2n. So what I'm going to do strategically, right? Plan in advance. This guy here, I'm just going to turn that into 2n. 2n, right? And that is the term with 2n, which means the coefficient that they really want is this guy. So therefore, coefficient of x2n is 4n, 2n. Yeah, part 1, done. Now, that there is good because you can sort of see it, right? The plan is that guy there is the left-hand side of part 3. I'm expecting that somewhere in here, right? That will give me the string of numbers for the right-hand side of the thing I have to prove in part 3. So that's the game plan. Now, I like part 2. Part 2 looks hard, but it isn't really. Once you sort of crack a few nuts here, right? First thing, they went from 4n to 2n. Yeah, how? Right? Why? For those that are quite cluey, they can sort of see the expression inside. Now, normally we have 1 plus x. This one here is 1 plus x. Now, those terms in there are not coincidental, right? They're not just random numbers. X squared plus 2x plus 1, that is a perfect square. And if you can see that, then what you're effectively saying here is this guy is like 1 plus x squared to the power of 2n. That's how it becomes 4. That's how it links to 4n, right? So essentially, this expansion here is the same as the green, right? Is the same as the green. This is the same as the green. That's important because now I'm basically re-expressing the green in a different way that would then give me a different expansion. At the end, it feels like I'm going to compare the coefficients of x to the power 2n to get my final answer. So let's go down this path now. So a smart thing to do here would be to maybe group these two terms as one so I can get the same binomial expansion, right? So for part 2, smart thing to do 1 plus. Now, when you group them, maybe worthwhile factorizing x as well. Yeah, and then use your blue binomial expansion here upstairs to expand this. Now, be very careful here, right? I'll tell you this now, right? I'll tell you this now. If you did not, let me do it, right? I'll show you what I mean. You won't prove what you have to prove. Now, just to be clear also, the thing that I want you to prove here, right? What is that really? That is basically saying, right? That is basically saying when you sub in 0, you get 2n 0 x to the power of 2n minus 0 times this guy, x plus 2, 2n minus 0, plus 2n 1, x, 2n minus 1, x plus 2, 2n minus 1, etc., right? That's really what it means where you go all the way up to 2n, right? So that's just a lazy way of writing a string of numbers, right, in the expansion. So let's expand now. I'll tell you why people do the next part wrong, right? Check this out. So when I expand it, just like upstairs, look what I get. I get 0 plus n1. Now, this is like one term, right? Picture this like one term. So then you get plus x plus 2 to power 1 plus n2 x squared x plus 2 squared plus. Now, why is that wrong? Or why is that not what they want? Look at this. Oh, sorry, there should be 2n there. Yeah, 2n. Now, why is that not what they want? Look at the powers, right? 2n2, oh, sorry, maybe I'll go 2n1, 2n1. That power is different to the 1 over here, right? Yeah, I have a power of 1 here. They want 2n minus 1. So what have they done, right? Or what do they want you to do? They want you, instead of expanding this in this form, they want you to reverse the terms, right? So don't do it this way. Instead, expand this like this. Yeah, because then that reverses you. Not that it matters because it's symmetrical, but that's how they want you to expand it, where the first term, like 2n0, gets this guy to the power of 2n, x plus 2, power of 2n. Can you see now? The powers are lining up, right? The powers are lining up. So that's 2n1, x, 2n minus 1, x plus 2, 2n minus 1, right? The powers are lining up. And that's exactly what, and I know that the final term, just for completeness, so when 2n, x is gone, right? So I'll just put a 0 there, and then x plus 2 to power 0 as well, yeah? Because then I can then abbreviate and summarize this guy in the summation form, right? Equals to sum from 0 to 2n of the notation. Now, how do you know? Yeah, how do you know what k is in this case? K is a term that basically increases in value as you go from left to right. Look at this, right? 0 there, minus 0, minus 0, 1 there, minus 1, minus 1, 2n there. I mean, that is like 2n minus 2n, 2n minus 2n, right? So what's important there, it starts at 0 and it goes to 2n, right? Starts at 0, goes to 2n, where every term here then, right, where the k is. So if I said to you 2n, see the combinatoric term, that's a k down there, right? And then it's x, 2n minus, and that's value of k, right? And then there's x plus 2, 2n minus k as well. Yeah. So as part of the challenges, as part of the 2 marks, understanding the summation notation is quite critical, right? Now, that should give us sufficient, sorry, that's part 2 done, just to be clear, right? That should give us now sufficient information with the fact that's given in part 3 to do the final part. Let's see what they're trying to tell us, right? They're basically saying, oh, by the way, this thing that you proved upstairs, this thing here, without the combinatoric term, can be expanded to this, right? So that guy there can be expanded to this guy. Okay, now, what's that trying to say? Let's see. That's trying to tell me that this guy here, so within the string of numbers, there is another string of numbers. That's important. That's important because if I'm at each point here, right? Each thing, you know what? Maybe it's easier if I got rid of the pinks, right? Just so I can talk about this. Ooh, I can't have the highlight, so let me give it a highlight and then do it. There you go. The pink's a bit distracting. All right. So can you imagine now, right? Can you imagine, can you envisage that for each one of these parts here, yeah, each one of them, they represent a whole string of numbers, right? So with each one of these, I have a combinatoric term in front, and it's multiplying by a whole string of numbers. Because what I'm going to do now, right, to make this whole question work, I already have from part one the coefficient of xn. If I can pluck out from each one of these blue terms the coefficients of xn, and I multiply with the green coefficient in front, I get the string of numbers that represent the coefficient of xn. So let me show you what I'm talking about, right? This guy is telling me, yeah, that, so for example, right, let me give you a demonstration. I'll do it in blue, right? So for part 3, let's demonstrate. Yeah. Now, when k is 0, so for this term here, when k is 0, right? When k is 0, I'm going to sub k is 0 into all the terms on this side here. So I got x to the power of 2n, right? So this is the left-hand side I'm subbing into, x plus 2 to the power of 2n. That equals to, sorry, let me zoom in for a second. I'll write a bit neater when I'm zoomed in. Yeah, let's sub in 0 to k, or for that expression there is 2n 0. What's that? 2 to the power of 2n and x to the power of 2n, right? Plus 2n 1, right? 2 to the power of, what's that? 2n minus 1 and plus 1. Yeah. So x to the power of 2n plus 1. Be careful there with the plus there. Yeah, that guy there is a plus. Yeah. Plus dot 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 plus. Now, go through this process. Don't skimp on the detail. You need this, right? So the last term there, 2 to the power of 0, x 4n minus 0, right? So you can see that this expression gives you a whole string of numbers that start from, it's like a polynomial there, right? Starts with 2n, goes all the way to 4n, right? Yep, that's cool. Now, what are they after? Because keep in mind, right, at the end of all this, I have a combinatoric term over here that needs to multiply with all these terms here in this string. And what am I trying to pluck out? I'm trying to pluck out the coefficients of x to the power of 2n. So when k equals 0, I get this green term multiplied with this guy here, right? This is a constant. Yeah. So I've got my first one. So remember in the last lesson when I did comparing coefficients, I've got a whole string of numbers and I compared rainbows, right? That's my first term in the rainbow. That green term there multiplied by this pink term here, right, gives me my first coefficient of x 2n minus x to the power of 2n. Now we do the next one, right? When k is 1. So when k is 1, I similarly sub in everything. So x to the power of 2n, right, minus 1 is times x plus 2 to the power of 2n minus 1. So wherever you see k here, sub in 1. So 2n minus 1, x 2n minus 1. Yep. First term. Now that's not the term I want. I probably want the next term, right? Let's have a look. So it'll be 2n minus 1, 1, 2. Now when I sub in 1, there will be 2n minus 2. And on the x term, which is the one that I really care about, it'll be 2n minus 1 plus 1. So that's 2n, right? Perfect. That is the term I want, right? 2n. So spot that term, right? Plus, now the last term is going to be 2n minus 1, 2n minus 1 as a combinatoric term, and then 2 to the power of 0. And it'll be x to the power of 4n minus 2 times k, which is minus 2. Yeah. So you can imagine, right? What am I after? I am after this term here, because in this next term on the expression, I got my green term here. I got my combinatoric term, and it's going to multiply with this whole string of blue values. So then green term times, if I wanted to pluck out the coefficient of 2n minus 1, it's this guy, right? This is the constant that the green will multiply with this part of the pink. And so on and so forth, right? So let me see. So the last term that I get stuff is this when k equals to 2n, right? So let's go there. Let's go ... when k equals to 2n. It feels like this is the last term. Now, let's see. I'm not even sure we get a term, maybe. Yeah, let's see. 2n. Maybe I do. Or, do I even need 2n now? What am I after? 2n sounds too large. Let's see, 2n. I just need, see, the last term here is 4. Where is it? Sorry. It's going all over the place. Yeah, this guy. The last term is 4n minus 2k. Now, for 4n minus 2k to equal to 2n, what do I need k to be? That's like 2n equals to 2k. K equals to n. I need k equals to n actually. Not 2n is too large, right? 2n is too large. I do not need that. I need, so let's adjust that to k equals to n. That will be the last term that where a x to the power n term is available, right? So let's do this. So when k equals to n, let's see what we get. We get x to the power of 2n minus n, which is n. Maybe I'll just write it as n, times x plus 2 to the power of 2n minus n as well. All right. And then I'm gonna, let me scroll. I'll start off over here and I'll subtly move to the right. Here we go. So wherever there's k, just replace it with n. So this would be 2n minus k. So 2n minus n, that's n, 0. 2 to the power of 2n minus n, so that's n, and x to the power of n, right? Plus 2n minus n, so that's n1. To the power of what's that, n minus 1 is x, n plus 1. And I know, because I solved it in the pink, that when I sub in n into the last term there, that'll be n to the power of 0, x to the power of 4n minus 2n, that's 2n. Perfect. So when k equals to n, I get my last term, right? I get my last term that multiplies. Now, it basically means when 2n is here, I don't get a term that's matching this. So I'll show you what I mean by that. So let's see, x 2n to 0. This is the term I want, and this will multiply now. So for this string of for these strings of numbers, the last term there would be too large. I'm just going to move it to the right. So somewhere in the middle, when k equals to n, right, and that gives me x 2n minus n x plus 2. Actually, you know, let me just straight copy that down here. So 2n minus n is n x plus 2 n. Right? This guy here is this term here. That's the last time I'm going to get a power of x to the power of 2n, right? Where the combinatoric term of the green term there multiplies with this string and gets with this guy, right? So everything else above that is not going to give me a coefficient of 2 to the power of x to the power of 2n. It's too large, right? It's too large, don't want it. So what's my answer? Based on this, I'm going to get, if I say to you know, the marker or the teacher, comparing by, maybe I'll start here. I've got space. Let me see. By, or maybe I'll start with the equivalent statement. Since 1 plus x to the power of 4n equals to 1 plus x squared plus 2x to the power of 2n, right? Since the green here equals to the blue here, right? By comparing coefficients of x to the power of 2n. Now I know the green one, right? I did that in part 1. That's 4n, 2n, right? Perfect. Now the blue one. For the blue, it's going to be a combination of green times pink, right? What's the pink? This bit here. And this bit here, just the coefficient, right? Just the coefficients. So it'll be now, I was hoping, maybe I'll just delete this now, because I reckon I need about 2 more lines and I'm sweet. Let me just move this up so I can fit it all in the same slide. Perfect. Okay, perfect. Now let's go green times pink, right? So the green first term there is 2n0 times 2n0. Oh, is that what I want? Let's have a look. When k0, 0. Yes, perfect. Yeah. And then there's a 2 to the power of 2n there as well. Good. Look at that, right? When k0, 2n, 0, 0 is perfect. Plus next green times next pink. So let's see if this works. 2n1, 2n minus 1, 1. Now, does that work for itself? So 2n1, 2n, perfect. And then this one here times 2n minus 2. Yes. Plus dot, dot, dot. Now, I know my last one, right, is 2n n times 2n minus, sorry, 2n, oh, no, times n. Now, let's see if that works. When k is n, that's 2n n, yes. And 2n, yes, perfect. And then 2 to the power of 0, which also works because 2n minus 2 is perfect, right? So once I have this, I can say to my teacher, that is exactly this guy where the k values, right? I mean, where are the k values, right? There, that's what's changing. This guy's changing. Technically speaking, this is minus 0, and this is minus 2 times 0, right? And this is 1, 1, 1, and this is like 2 times 1. This is n, n. Oh, this is like 2n minus n, right? And this guy here is 2n minus 2n, right? Perfect. So then I can say, which equals to the sum, right, of 0, or maybe go k equals 0, and 2n. And then I'll write in my notation here, 2n minus 2k, 2n, k, 2n minus k, k, boom. Damn, that was a hard question, wasn't it? Yeah, it was a nice one though. I like the fact that it turns people off, right? Just with the notation itself, but there you have it. Guys, I'm going to embark on one more question, right? HSC 2009. Now, this question, once again, I think the diagram is really what throws people off, but let's have a look at it. It's worth 8 marks. You can see there. I think this one here, technically speaking, is easier than the one before. Easier, but it's an application question. So let's have let's explore it a bit, right? So, show that the geometric that's a GP, right? Hence, show that. Cool. Consider the square grid. And then I got to prove some stuff and then prove a final idea. Okay, cool. Now let's do this, right? Let's dive right in, right? Let's not waste any time. The first part, sum the geometric series. Now it looks like it's a GP because it's got a common multiple, right? So I know that the sum of the GP, right, equals to, I mean, what's the formula here? Sn equals to A. Now, which one do they want me to use? I don't think it matters, right? Maybe I'll just use the R because it's bigger than 1, n minus 1, R minus 1 formula, right? Just to help us with this. Then what you get A, which is that term there. So I'm assuming it goes that n is higher than that. Yep. So it'll be A times R, which is 1 plus X. Now, how many terms are there? It'll be n minus R, right? Yeah, n minus R terms. minus 1 all over. I'm hoping this is what they want to do. Yeah, it is. Plus r minus 1. Yeah, so then this equals 2. What's that equal to? So let's simplify that. X r. Look at this. Look at this. I'm going to do two things. One, that becomes x, right? Two, using rainbows, this guy times this guy, right? What you get is, I mean, if you look at the algebra here, if I have like a to the power of r times a to the power of n minus r, when you add the powers on top, the r's go away, right? So in this case, you get 1 plus x, r's go away, so power of n minus 1 plus x to the power of r all over x, right? Yeah, now, if this expression here equals to this expression here, how do I show this? It looks like they've compared something, right? This one has a string, this one has a term. It looks like they've compared some sort of coefficient. And I believe if you look at, I mean, exploring, so let me go back to the original, right? I'm just going to put a few formulas here. If I look at this guy and replace everything with R for now, right, for visual purposes. Yeah. Look at this. The first term is 1 plus x to the power of r, and I've got this coefficient. Where does that occur? It occurs when I compare the coefficient of xr, right? So I'm going to say, if I pluck out all the coefficients of x to the power of r from all these terms, I'll get the left-hand side, and then I'll do the same on the right. So here's what I'm going to do. Therefore, since 1 plus x to the power of r plus 1 plus x to the power of r plus 1 plus dot 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 1 plus x to the power of n equals to the thing that I just proved, 1 plus x power of n minus 1 plus x to the power of r all over x. By comparing coefficients of xr. Right? This is why it's 3 marks, right? I need to work for this of xr. This guy here, right, has a coefficient. It's the last term, so it's r. This guy here has the coefficient of xr to be r plus 1, choose r, right? It's just the r plus 1 term, right? Plus, then this guy here would have the coefficient of n r, right? Assuming n is bigger than r, right? Yeah, and this side now, how do we work this? I know, right, that the coefficient of xr here and the coefficient of xr here is not what I want. Why? Because I'm dividing by x. Because I'm dividing by x, I need both of those. Actually, I'll do it in a different color just to talk to it. For the greens, right, I need both of the greens to give me coefficients of x to the power of r plus 1. So it's 1 bigger, because when I divide by x, it becomes the coefficient of xr, right? Does that make sense? Right? Because I'm dividing by the x, I need both of these to give me, so I know, right? Say, for example, this guy. This guy's going to be expanding to this, right, with the power of n. I needed to go n1, n0 plus n1x plus dot 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 plus n xn. Now, I know that r is somewhere in between here, but that's not the one I want. The one that I want is n r plus 1, right? That's the one let's see, actually. Have I? Let me just make sure I've done this right. I don't think I've done it right, actually. How many terms are there? I think that expression there isn't right. How many terms are there? So if I had n terms, let's say that was 10 and that was 1. when that's 1 to 10, that's 10 to, I need to add 1. Because if this was 10 and this was 1, I don't just subtract it, right? Because when I subtract that, that's 9, but there's actually 10 terms. So what's missing in my expression, and I apologize for this, is really the number of terms should be +1. So that should be, when I expand it, that should be n plus 1. And the reason why I know that is because n plus 1 here, right? That's missing. So +1 there. So what really should be adjusting these ones all have +1 in them. Yeah, that's better, right? Because then, and the reason why that's important is because when I do this, I'm expecting then, so that's r plus 1. Sorry, let me write that better. I'll write that better, r plus 1. I'm expecting them by comparing the coefficients of xr. I take the xr plus 1. This is my coefficient, right? Yeah, that's my coefficient. Now, for this guy, it doesn't, the highest power it goes to is n, sorry, is r, sorry. Let me write that again. The highest power it goes to, that's r, is r, x to the power of r, right? Plus dot 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 r x r. It's too small, right? There is no term, when I divide by x, there is no term that has xr in it, right? So in other words, the coefficients for this one don't matter. It's all to do with this guy here. So therefore, n plus 1, r plus 1, right? That's the key for this term. And then I've done it, right? That is the proof, right? So your teacher would like to see you break, I suspect the marks are allocated 1 mark potentially for the GP expression, and then 2 marks, 1 for the left-hand side having the string, and 2 for the second one for the n plus 1, r plus 1 term. Yeah? Cool. Now, let's apply this, right? So once you get that, hopefully we get to use it, right? That is the point. So in part 2, consider a square grid with n rows. So there's n rows down here, right? And n columns, right? So yeah, that sort of reverse the description. That's n rows, and same thing. Several intervals of gradient 1, whose endpoints are the points, are drawn. Okay, cool. These are all gradients of 1, 45 degrees. Explain why the number of such intervals on the line y equals to x is that. Now, they want you to basically go, y equals x is this one, right? Yeah. Why does that one have intervals, the number of intervals equivalent to this? The best way to explain it is, how do you draw an interval? You need two dots, right? You need 2 dots. How many dots are there on that line? Now, I know it's an n by n grid, so this must be n dots. From n dots, choose 2. That's what they want, right? So for this one here, all they want you to say for part 2, question 1 is, on y equals to x, there are n points. To make an interval, 2 points are needed. Right? Therefore, number of intervals equals to, from n, choose 2. Right? Piece of cake. Yeah? Nothing too hard about that. Now, explain why the total number of such intervals on the grid, right, all those diagonals going that way, are equal to that. So the way you sort of envisage this is, when can you start making, you can't make an interval there, right? That's impossible. The first time you can make an interval is here, right? So from this one here, from 2, choose 2, right? Let's write in there, choose 2. From this one, that one there is from 3, choose 2. This one, 4, choose 2. Blah, 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 right? Dot, dot, dot. And this one here, n, choose 2. And then it dials down. So you can sort of see they dial up and then they come back down, right? That makes sense because it's symmetrical. Yeah. So explain why. So Now, how would you say this? So the intervals start at n equals to 2, right? And it goes to n equals to n, right? Right? So it starts at n equals to 2, goes to n equals to n, and then back down to n equals to 2, right? Where there's only one of these in the middle. So therefore, now there's only one mark, right? So it doesn't matter which sort of, it's really to do with the language per se, but the concept, right? So if you can demonstrate to your teacher that you know the concept, right? Therefore, the sum of all intervals will be n choose 2 plus 3, sorry, not n choose 2, choose 2, 3, choose 2. So the diagonals increase plus all the way. Now, they want you to show 1 before it. That's important, I guess. Plus n. Now, this bit here covered the intervals from here, including the middle one, right? And then they go, it dials down, right, for n minus 1, right, symmetrically, 3, 2 plus 2, 2, right? Which, I mean, I'll color code it, but I'll get rid of it in a second. Represents the second half, right? That makes a lot of sense. Done. So let's get rid of colors. It's a bit distracting, that's all. Yeah, that's done. Now, that's question 2. A lot of people consider that to be a hard part because it's an application. You got to sort of glean from the diagram what this is trying to say. Once you've done that, we basically put part 1 and part 2 together algebraically. Guys, I'm just going to copy this slide here, and I'm just going to remove the things we've already proven because we no longer need it to do part 3. Let's see. Cool. Part 3, so it's a nice question that puts it all together. Using part 1, show that this now. What do we know? We know that Sn equals this, right? And then we also know that from part 1, that whenever I have a string of numbers, I can use this simplification. Now, how do you look at this, right? Look at this. This is how I want you to see it. R, the bottom number there, you can sort of see what on this side, right? If the bottom number is R, in this case, R is 2, right? In this case, say it stops at N, right? There. In this case, R is 2, and the top number N, well, N is N, right? N is N, good. Oops. N is N, yeah? And then for this side here, the only difference is R is still 2, right? The bottom number is 2. The top number, though, is N minus 1. So when I go and sub in the top number there, right, I'll use N minus 1. So I won't do this N equals to N because it's a bit confusing, but I use N for the first one and then N minus 1 for the second one. So it feels like for part 3, I say to myself, Sn equals to, right, 2 parts, blue and green. For the blue, I'm going to use this formula and use this side, right, by subbing in R is 2 and N is N. So R is 2, N is N, so N plus 1, and R is 2 plus 1. Yeah? Plus, so that's the blue. And now for the green part, I'm going to sub in N minus 1. So N minus 1 plus 1, that's N. So N minus 1 plus 1. And once again, 2 plus 1, right? So just to be clear, this bracket is this. This is this, right? Using part 1's formula. Once you get that, it's just algebra, right? With combinatorics. Let's see. Let's see if we can break this quite quickly. So that's like N plus 1, 3 plus N 3, right? Now, they probably want me, yep, if they want me to as a fraction, they want me to do it in factorial form. So that's like top factorial bottom factorial, top minus bottom, so n plus 1 minus 3, n minus 2 factorial, top factorial, bottom factorial, top minus bottom. Feels like there's a bit of common denominator action required there. Now we know that n minus 2, n minus 3 is smaller. So if I multiply this by n minus 2 and n minus 2, that should give me the same common denominator, right? Then it would be 3 factorial, n minus 3 factorial, and the top would be plus 1 plus n minus 2. Now, let me get rid of these arrows. Move this up so I have space. Now, what do I want? They got 6 on the bottom. So basically, a few things happen here, right? Firstly, this is 6. Feels like this is going to cancel out there. Feels like I also should probably factorize. Because I know that n plus 1 factorial is equal to, this guy here is n plus 1 times n factorial. So if I factorize n factorial out, hopefully I get what I want. Right? No. See how they want me to cancel out n minus 3. So yeah, no, still works. So I'm going to factorize n factorial out. This becomes n plus 1 plus n minus 2 over 6 times n minus 3. I was going to do 2 steps in one. Yeah, because right now I'm going to clean this guy up. What's that become? M equals to 2n minus 1. Good, because that's that bracket there. Second thing. Now, why do I feel like I've got an extra bracket? Just give me 1 second to make sure that I'm not doing this wrong. Top factorial, bottom factorial, top minus bottom. I feel like I should be fine. It'll be it's n minus 1, n minus 2. Why do I have an extra bracket? N minus 2. Let me just check that I've not done that wrong. You know why? N plus 1 minus. What have I done here? I've done something wrong because I've got an extra bracket. So n plus 1 minus, that's n minus 2. Yep, that's this one. Top factorial, bottom factorial, top minus bottom. Is that right? Plus 1. I've done something silly there, haven't I? It'll be n plus 1 and n minus 1. Yep. N minus 1 minus 2. Sorry, give me 1 second. I'm just trying to see. There's n plus 1. What have I done? I've done something silly because that n factorial should be, that should be n minus 1 factorial, but I'm trying to see why. Let me see why. What have I done algebraically? So let me take a step back. All right, let me take a step back. Looks like I've top factorial, bottom factorial, top minus bottom, top factorial, bottom factorial, top minus bottom. To get to that, times top of that. Cool. I get that. That is the same. Silly. Okay, I did absolutely everything right. It's just that when you multiply this should be a 2. Should be a 2. Perfect. Okay, cool. Nice work, Ricky. Nice work. N minus 1. So I'm gonna do 2 things. This guy becomes that. What I should do also is change this guy into n times n minus 1 times n minus 2 factorial. Because then that goes away with that, right? Beautiful. Therefore, that times 2n minus 1 over 6. Done. Apologies for that little hiccup in terms of algebra. that's how you do it now. So this question was a little bit harder, purely from the perspective that it's an application, right, where there's a diagram and a lot of people get caught up in this bit here. Although, I guess I say this to my students a lot. The first part there is just GP. The last part, 3 marks, even if you couldn't do the 2 marks in between, it tells you to use it. You could have easily, right? Not easily, right? But you could have used that and the expression that I used in here to do part 3 without doing part 2. So I guess what I'm saying is, when it's a 3-parter like this, look at the 3rd part. If you can't do the middle part, still persevere and use the 2 parts before that. Guys, that's the video that details 2 questions that are harder. If you like that video, please give it a like, subscribe to the channel, tell your friends. That's it for binomial theorem identities. On to the next topic next time. I'm still in the process of selecting it. If you have any ideas, feel free to comment on the channel and let me know what topics you want. But otherwise, yeah, I'll see you guys later. Thank you.